So as we start the remainder of Chapter 13, we're going to understand how it is that intermolecular forces of attraction determine the properties of liquids and solids. So we'll start first with section 13.2. What are those forces of attraction? Now before we can start, we have to define the difference between intramolecular and intermolecular. Intramolecular means forces that are within, such as the forces between covalent, ionic, or metallic bonds. But intermolecular means between two different molecules, and that will include the three that we will learn: dispersion forces, dipole-dipole interactions or forces, and hydrogen bonding. Kind of a misnomer, it's not really a bond. So if we look at a picture of this, I think it will become quite clear. Notice that the intramolecular force is referring to a bond within, in this case, a molecule. But the intermolecular force is symbolized with a dotted line, and it represents a much weaker force of attraction between two different molecules. Now, intermolecular forces come in three flavors. We're going to start with the first two, and then I'll stop the vodcast. Please recognize that when you are done, having completed the worksheets that deal with section 13.2, then you will be taking a quiz on distinguishing between the three types of intermolecular forces, so pay careful attention. Now, a dispersion force is sometimes called a temporary induced dipole. Write that one down. One more time, temporary induced dipole. I'll explain that. And that's a weak force that happens because, for reasons we can't really explain, all of a sudden you might see a shift in the electron clouds. And what this can do then is create a temporary polar molecule or atom, which has a temporary weak force between the two different atoms or molecules. So let's take a look at a picture of this. One part of that molecule will become kind of negative, the other end will become kind of positive, and the oppositely charged ends will be temporarily attracted to other partially positive, temporarily so, molecules or atoms. So that's a mouthful. Let's take a look at this picture. What I want you to consider is these are two helium atoms, 1 and 2, and this is the before picture. Notice they have spherical electron clouds, nothing's gotten distorted. But for reasons we can't explain, all of a sudden helium atom number 2 says, I'm going to switch all my electron clouds off to the left. Well, when that happens, electrons repel other electrons, and so when these electrons start pushing to the left-hand side of its molecule, it pushes away the electrons on another cloud nearby on a different atom. Then what happens is this: the end where the electrons travel to become partially negative, and the end where the electrons fled from become partially positive. One atom started it and made the other turn into a dipole. That's the induced part. The word dipole comes from the fact that for just a fraction of time, they'll have a positive and a negative end. And they're temporary because it doesn't last. And now there is a force of attraction between the kind of positive end of one atom or molecule and the kind of negative end of another. And that's what a temporary induced dipole is. It's the weakest of the three intermolecular forces, but it's very important, as you will see in just a moment. It actually has a direct impact on the strength of the intermolecular force, which has a direct impact on the state of matter. And there's an interesting trend, if you notice, as the molecular weight, let's go down the halogens, from fluorine down to iodine. As the molecular weight increases, you go from a gas to another gas to a liquid to a solid at room temperature. The greater the strength of those London or London dispersion forces, or sometimes they're just called dispersion forces, the greater the strength of attraction, the more likely your matter is to be a more organized form of matter. Now, how do I know iodine has the strongest force of attraction? It has the biggest molar mass, which means it has the most electrons. The bigger your electron cloud, the greater your London dispersion force. And how can we measure that in the real world? By measuring the boiling point. You will see in this chapter that we use boiling point to indicate the strength of intermolecular forces. The greater the boiling point, then that means the more energy it takes to break apart those forces, not bonds. Don't call them bonds. To break apart those forces. So fluorine to iodine, as you go down, molar mass increases, the size of the electron clouds increase. When they shift from whatever direction to the next direction, they have a larger cloud, which causes a greater strength of attraction, which accounts for a higher boiling point. And that's why dispersion forces are very important. An important thing to understand, though, is that a dispersion force just lasts for a nanosecond. That's why we call it temporary. And what will happen is atom number 1 will go back to being normal, but maybe atom number 2 will induce another atom or molecule nearby to also turn into a dipole, temporary. And so you have this chain reaction going on inside that soupy mix of atoms or molecules, where constantly dipole interactions are temporarily being created, usually in nonpolar substances. So forces with the greater molecular size and weight, I'll go with molecular mass right now, will have a greater dispersion force because they have a bigger electron cloud. Now there's another factor that impacts the strength of a London dispersion force, and it has to do with the shape of the molecule. Specifically, that factor is surface area. Let's take a closer look at this picture that again is worth 1,000 words. Now with a quick glance down at the bottom, see how the N-pentane has a 309.4 boiling point in Kelvin, and the neopentane has 282.7. They weigh the same because they're made up of the same number of hydrogens and carbons, and penta means 5, so there's 5 carbons in the middle of both of these guys with a whole bunch of hydrogens attached. What's different is the shape. I call the N-pentane, this is an isomer, a same number and kinds of atoms, but a different arrangement. I call these a sausage shape. And see how there's lots of surface area between the two more linear molecules for London forces to occur. But the neopentane is more spherical. It has less surface area, less possibility for these London dispersion forces to occur, and that's why their boiling point is lower. It would take less energy to break the forces, not bonds, between the neopentane compared to the N-pentane. So shape, which actually dictates surface area, is the second factor that impacts the strength of a London dispersion force. All substances have London dispersion forces, but there's another kind of force that they may also have called a dipole-dipole force or interaction. Primary difference: it happens between two molecules that are permanently polar. And why are they permanently polar? Because they don't share their electrons evenly between two atoms within a molecule. Let's take a look at this. So I would rather show you the picture of this, and here we go. Here are some molecules. This is a molecule, that's a molecule. The reason why there's a negative sign at the end of this molecule and also the other one, and a positive sign there, is because on the red side of each molecule, there's an atom with a greater electronegativity. Remember, electronegativity means that you're a bigger hog of electrons. So within that molecule, they're sharing, but on the red side, that's where you're going to find more electrons. And that's why it makes the red side of each molecule permanently, not temporarily, negative. On the right or blue side, then, there's a partial positive charge. Remember, this isn't caused by the electron cloud suddenly shifting. It's caused by a permanent separation of charge caused by differences in electronegativity. Well, now you can see that within a soupy mix of molecules, all the same charges, two negatives or two positives, symbolized with the dotted lines, the molecules arrange themselves in such a way to try to minimize the like charge end repelling each other. And then they try to maximize shown with the solid line, the attractive forces between two oppositely charged ends. So the more polar an individual molecule it is, the stronger the dipole-dipole force, not bond, between them. So be careful, that's a force. Within the molecule, it's a bond. But between two different molecules, that's a force, the dipole-dipole interaction. Now let's take a look at dipole-dipole interactions. I purposely have made a graph here, a table here, showing a bunch of molecules with about the same molecular weight. So what you can conclude then is they must have, since everything has London dispersion forces, the same amount of dispersion forces. So that doesn't explain then why all these different compounds have very different boiling points. Remember, the higher the boiling point, the greater the strength of their intermolecular force of attraction. Well, what happens as we go down this chart, the strength of that dipole-dipole force increases. And why is it increasing? It's a funny unit. Don't need to know. It's called the debye. Why is this debye a number that shows how strong the dipole-dipole force is? Why is it increasing as we go down? Because acetonitrile, CH3CN, is much more polar because within its molecule there's a much more uneven sharing of the electrons. Hence, there will be a stronger force between two molecules of acetonitrile than there would between two propanes, which are fairly nonpolar. Okay, so I think we just said that, and that's what's summarized here. The most polar molecules will have the strongest attractions. Another generalization would be the reverse of that. If you have very different molecular weights, then dispersion forces have the greatest impact on the boiling point or the strength of the intermolecular forces. And as we said, the bigger the electron cloud, the stronger the temporary induced dipole can be found in a substance that has dispersion forces. I'm going to stop there, and we will pick up next on the subject of hydrogen bonding, which will go hand in hand with a worksheet called, amazingly, hydrogen bonding. Remember, you will have a quiz on the differences between the three forces, being able to describe how they occur and what is their relative strength to each other, being able to compare and contrast them. I'll stop here. You have a worksheet, a study guide that directly connects to the section on the chapter in chapter 13 with intermolecular forces.